So this week we're going to talk about reaction rates and how they vary with temperature. And so to do that, we're going to get yet another equation out. This is going to be different from the first order rate laws, second order rate laws, all that kind of stuff. We're no longer going to be concerned too much about reaction order. We're going to be more concerned once we find K, how if we vary the conditions of our reaction, how does that affect the rate, right? Because not all chemical reactions are run at the same temperature. So we're going to be focused on temperature today. What I want you to watch as we do this, I'm going to do a little bit of kind of deriving of formulas and stuff and talk about the information behind uh, the equation, the Arrhenius equation that we're doing today. But what I really want you to take away from this and recognize is what are the variables that are in this equation and how are they different from the variables that we saw in other equations? Because there will be things that are the same, like the rate constant, right? When we're talking about rates, we'll always have a rate constant for our reaction, but there will be a lot of things that will be different as well. So things that like temperature, um, activation energy is going to be a brand new concept that we're going to introduce into this thing. So knowing what activation energy is, knowing what temperature, when temperature shows up, right? So if you see a question that has multiple temperatures in it, that's a clue that you're going to be doing the kind of equations that we're going to develop and work on in this video. Okay, so pay attention to that. And we're going to talk a little bit about what are the things that affect the rate and what makes it speed up, what makes it slow down. So you'll also get a little bit of that. So pay attention to that type of thing as well, because that can be useful as we go forward. It'll also help you just kind of get a good sense of what reactions do. So what we're looking at today, our main idea is that reaction rates change with temperature. And I think this makes, kind of intuitive sense because if we think about it, if we heat up a reaction, we would expect it to run faster. But what we want to maybe take a moment to think a little bit more about is why does that happen, right? What is happening in that chemical reaction that's allowing it to heat up or that's allowing it to go faster once we heat it up, right? So obviously, if we increase temperature, we're adding energy to the reaction. Increased temp equals added energy. And so when we add energy to our reaction, there's a bunch of things that are going to happen. One, the molecules are going to start moving faster, right? And two, they're going to run into each other more. So equals added energy equals increased number of collisions between molecules. And those collisions are going to be more energetic. Collisions are more energetic, meaning that the molecules that run into each other have more energy as they add together. This is the idea of activation energy, right? So reactions occur when molecules, and we won't put a number on how many molecules because it depends on the order of our reaction, but it occurs when molecules collide with enough energy to make or break bonds. So in your normal everyday room temperature reaction flask, you have molecules flying all over the place and they bounce off of each other, into each other a whole bunch of times. But only a certain percentage of those collisions result in actual chemical reactions where A plus B turns into C, right? Where they stick together or they fragment apart in a slightly different way, right? So not all of those collisions result in reactions. And the reasons for that, there's a couple of different reasons for that. One, sometimes they just don't have enough energy, right? If they just kind of gently nudge into each other, that's not really going to impart too much energy from one to the other. They're not going to stick together. They're not going to share electrons to hold on to it. They need to run into each other with enough energy to overcome that kind of instinct to just kind of stay as they are, right? So slow collisions are going to bounce off each other. Fast collisions, there's going to be energy that's imparted between those reactions and can be right? It can result in sharing electrons, breaking bonds, right? Maybe they don't share electrons anymore, breaking bonds, that kind of thing, right? This is the activation energy, right? This idea right here is the idea of activation energy. Activation energy is how much energy it takes to make sure that the reaction takes place. Activation energy is that amount of energy, right? So where I said enough energy here, I meant they collide with at least the activation energy or more, right? As we increase the temperature, of course, we're more likely to be above that activation energy because the molecules in general are more energetic, right? And that means that that makes the more or larger percentage of the collisions result in reaction, which means that the rate is going to go up, right? If you have a higher percentage of collisions resulting in reaction and you have more collisions happening, it only stands to reason that our reaction rate is going to increase. All right, so that's the conceptual idea. The Arrhenius equation takes that conceptual idea and actually puts numbers on it. And it says, well, your reaction rate is going to increase with temperature, but that increase we can describe mathematically. And so that increase, here's our rate constant, K, right? We remember our rate constant from all our rate laws and such, right? That rate constant equals A, we'll come back to A in just a minute, times E, which is just the logarithmic value, raised to the power of the activation energy divided by RT. All right, so EA is the activation energy, which we just defined. T is, of course, temperature. And R is the gas constant. Right, so R just kind of shows up in here. A, this big capital A over here, this is called the frequency factor. And this will be different for each reaction, but we're also going to kind of drop A out of this equation here in just a minute. So I'm not going to spend too much time describing the frequency factor. The frequency factor basically boils down to how often do molecules collide in such a way that the reaction is allowed to occur, right? So if you have water, for example, water has, let's say that it has oxygen here, hydrogen's up here, right? So H2O, you have oxygen here, hydrogen here. If your reaction requires the hydrogens to bump into something in order to occur, not all the collisions are going to result that way, right? Sometimes the collisions will be the oxygen running into something else, right? And those will never result in reactions, no matter how energetic they are, because the right thing isn't running into it, right? The reaction is occurring at the hydrogen atom, not the oxygen. But some of them will be, right, the correct way around, and then we have to worry about temperature and activation energy and all that other stuff. But this difference between, right, the orientation of the molecule, is the oxygen oriented, is the hydrogen oriented, etc., that's where the frequency factor comes in. But it's not something that we really calculate and or worry about too much, right? Like I said, we're going to do some manipulations to this formula to kind of really minimize the effect of this frequency factor. So for now, we're just going to acknowledge that it's there and move on. So this equation tells us a couple of things, right? It tells us that our rate constant increases, K, goes up when the temperature rises, right? So if the temperature goes up, because this is a negative exponent here, that means that this number is going to get closer to zero. It's going to get smaller in an absolute sense. So it'll get closer to zero. That means that E raised to a smaller negative power is going to get larger and larger. And that means that our rate constant is also going to get larger, right? So when the temperature goes up, this factor gets larger. That means that our rate constant also increases, right? When the activation energy goes up, our rate constant goes down, right? So the activation energy and the rate constant are inversely related. When EA goes up, K goes down. And this is the same argument, right? As EA goes up, this number gets larger or farther away from zero in a magnitude sense, right? It gets farther away from zero. And so that makes this, because it's a negative exponent, that makes this effect smaller, or this factor smaller, which means our rate constant gets smaller, right? So when EA goes up, the activation energy gets higher, our rate constant goes down. That makes sense, right? If the activation energy is higher, that means that fewer molecules are going to have enough energy to get over that barrier and do their reaction, right? The higher the activation energy is, the fewer molecules are going to reach that level of energy or win their collisions, and the slower the reaction is going to go. The lower the activation energy is, the more molecules there are that are above that energy. It doesn't take very much energy for the reaction to occur. So if you have a low activation barrier or a low activation energy, your reaction rate is going to go up because things are reacting more often because you have more molecules and more collisions that reach that barrier. Okay. So those are the two big relationships that I want you guys to see. The rate constant goes up when temperature goes up. The rate constant goes down when the activation energy goes up. Okay. Now we're going to look at the other forms of the Arrhenius equation. There are two of them. I'm going to rewrite the Arrhenius equation here. So K equals A times e to the negative EA all over RT. Right? Take the natural log of both sides. Ln of K equals negative EA over RT plus the natural log of A. And so now you can kind of see this is just a number, right? Whatever our frequency factor is, we just take the natural log of that, and this is just a number. And so, and this is a constant number for this reaction because you're always reacting the same things together. And so where this gets really useful, where the Arrhenius equation gets really useful is this form of the equation doesn't get used very much, right? Because if you're going to use this one, you would just use the first one up top. You don't have to worry about natural logs at all, right? So this one doesn't get used very much except if we want to compare. So this form, not useful except when comparing rate constants at different temperatures. Right? So we can calculate the activation barrier based on the temperature if we know the frequency factor and the rate constant. Right? So if you know your rate constant, and we know how to figure that out from experimental data because we did that with the rate laws, if we know our rate constant, we can figure out the activation barrier. If we instead we have multiple, well, so run experiments at different temperatures at T1, T2, T3, etc. Right? So run your experiment at a couple of different temperatures and then record the rate constant at each temperature. So your rate constants will be K1, K2, K3, etc., etc., right? So the rate constant at temperature 1 is K1 and so on and so forth. If you do that and then so you're going to have a whole bunch of different equations, right? We're going to put the T, we'll put the temperature in here, we'll put the K in here, T1, K1, T2, K2, etc., etc. And what we should have is we should have the same activation barrier throughout all of these. And so we can solve for EA and then set these equal to each other. And then we get a nice equation where we get the natural log of K2 divided by K1 equals negative EA over R times 1 over T2 minus 1 over T1. Okay. So notice this number is constant. So if we subtract two equations that both have this number in it, that drops out. And instead we just get K2 ln of K minus ln of K, which is going to be a quotient here. And we get EA over R. EA is a constant, R is a constant. The T, well, EA is constant across one reaction. And then the T's are going to be subtracted from each other. All right, so a couple of things here. Your temperatures need to be in Kelvin. Your activation energies are in joules per mole, and that means that your R value is going to be in joules per mole Kelvin. And so you can look up this value. The gas constant in joules per mole Kelvin is 8.3145. I think I've got that right. Oops, sorry about that. unless I messed up my, I got it right. Yeah, so 8.3145 joules per mole Kelvin. So you'll just plug that in for R, make sure that your units over here match up, and then you can solve this. Okay, yikes, I'm over 15 minutes. This is way too long of a video. Sorry about that. But that's the equation. Most of the time, you're going to use that third form of the Arrhenius equation, the ln of K2 over K1 equals negative EA over R times 1 over T2 minus 1 over T1, right? Everything in Kelvin, everything in joules per mole, right? Once you do that, then you can solve for a bunch of stuff. So we're going to do some examples in the next video. I'm not going to add that onto this one because this is already way too long. But stick around for that one. We'll get to do some math. We'll get to try some stuff out, and then we'll be able to use the Arrhenius equation to figure out activation energies, right? Remember at the beginning, I said I want you guys to notice what variables are in here. We have that was 10, 5 variables in this reaction. We have temperature 1, temperature 2, K1, K2, and we have the activation barrier. And so I can give you 4 of those 5 pieces of information in any question, and you will be able to solve, just algebraically, for the 5th one. Right? So watch for questions that say things like the reaction was run at multiple temperatures, right? You have multiple rate constants given in a reaction. Or anytime you see activation energy or activation barrier and you're given a value for that, immediately think Arrhenius equation for those. All right, so we'll do that on the next one. I apologize if this video went long. I have so much to say about the Arrhenius equation apparently. All right, see you in the next one.